Hello. In this video, we are going to look at solving double integrals over rectangles. Okay, so to introduce the topic, we're going to start off with a classic problem that's similar to the classic problem we dealt with in Calc 1, and that is how do we go through and find the volume beneath a surface and above the xy plane. So let's just draw a picture so that we can kind of wrap our minds around the problem. So here we have a surface. And beneath the surface, we have a rectangular region. So that rectangular region is defined by constants. So we have from A to B and from C to D. So A to B on the x-axis, C to D on the y-axis. And then we're trying to find the volume that's beneath the surface and above this rectangular region. So we can go through and sketch what that region would look like. Something like that. All right, so we want to go through and find the volume of this region. So how could we go through and do that? All right, so our goal, find the volume. Okay, so in terms of trying to go through and think about how we could do that, right, what you want to do is we want to go back to something that we already know how to do that's similar to this and then see if we could extrapolate from that. And so if you think about it for a few minutes, one of the things that should occur to you is that this is a similar problem to the Calc 1 problem that you encountered a few classes ago, where you were asked to go through and find the area under a curve and above the x-axis. So let's go back and take a look at how we did that and see if we could find any tools or methods or things that we could take from that and use to go through and try and solve this problem. All right, so let's go back and recall. So we want to go through and this is not find the volume, but find the area. And we can draw ourselves a picture. And let's just draw some curve here. This is y equals f of x. We have A and B. And our goal is to find that area. So how did we do that, right? So if you recall when you were taking that class. What you did is eventually, after thinking about it for a few minutes, you decided to go through and try cutting up this region, this area, into pieces, and then adding up the area of those pieces instead of just trying to figure out what the area of this all is all at once. So the pieces that we ended up using is we ended up using rectangles. So you could go through and create a rectangle, right? And then we could create another rectangle. And then another rectangle. We could just cut this region up into rectangles. Okay, and so we went through and we added up the area of those rectangles, and that enabled us to go through and find an approximation to the area that was between the curve and the x-axis, right? And then so after we did that, we went through and we tried to take that process and make it a little bit more formal. There was some way that we could go through and go from an approximation of the area to the exact area. And so what we did is we came up with the whole idea of the Riemann sum. And so that idea is basically the same thing that we're doing here. It's just kind of made a little bit more formal. You know, so what you do is you think about the idea of having a generic rectangle that's underneath this this region. So we're going to use this this rectangle here as kind of a generic rectangle. This one right here. And we went through and said, all right, well, let's say that rectangle is at x sub I. And we could say that the height of the rectangle is going to be f of x sub I. And that would be this distance here. And let's say that the width of the rectangle, actually, I'm going to erase this. The width of the rectangle could be change in x. Right, so, and then we could go through and say, let's find the area for that generic rectangle, and then we'll just vary x sub I so that it goes from one end to the other, right? And so the area of that rectangle would be f of x sub I. And then frequently, sometimes you see a star put here. The star stands for the fact that I put the x sub I here in the middle of the rectangle, but it could be on the left side or on the right side. Since the x sub I could be in different places depending upon the formula you use, you can put a little star there just to represent that fact. You know, so if you remember when you took that class, you can add up rectangles using the left-hand side of the rectangle for the height, the right-hand side, or the midpoint. So that's what the star stands for. It's just the different options. So we've got the height of the rectangle is f of x sub I. And then we've got the width of the rectangle is change in x. So this whole thing is the area of the rectangle is given by this piece. And then what we want to do is we want to take this representative rectangle, this generic rectangle, and we want to vary it across the region and add up all of the other rectangles. So the way that you do that is with a summation symbol. And then we can go through and take I and say it goes from 1 to n. Right? And so if you do that, what that's going to do is that's going to say when I is 1, we're at this first rectangle. I is 2, that would be the second. I is 3, that's the third. And then the last rectangle is the nth rectangle. And you go from I equals 1 to n. And then we're just moving this kind of generic rectangle here that we've got in the middle. We're just moving it across, and it represents all of those by just changing the I value. And then so if we did that, that would be just a more formal version of what we have up here, where I've just cut it up into pieces with rectangles. And then the last thing that you cover in Calc 1 is, hey, you know, n is going to be an approximation. If we go through and take the limit as n goes to infinity, then what we'll do is we'll end up, instead of having an approximation, we'll get the exact amount of area that's, you know, that's between the curve and the x-axis. All right. And I mean, we did some other stuff. I don't know if this is if this is relevant, but there's a formula for x sub I, a plus I change in x. Oh, actually, this is going to be relevant in the next section, so it's a good thing to review for sure. and then we get b minus a over n. So we do have formulas for what this represents and this represents. So anyway, this whole process is made very, very formal in Calc 1 through the Riemann sum. And then once you've built up this whole entire thing, we say, you know what? That's our notion of an integral, a definite integral. Is that this exact area that's under the curve that's defined by taking the area and then summing it up with infinite rectangles actually gets us the exact area. That's between the curve and the x-axis. Okay, so that's kind of the basics from Calc 1. That's what we did. We had this area problem. We thought about it. And we said, hey, let's just chop it up. If we chop it up, then we could add up those rectangles. And then once we had the idea to chop it up, we then made it really formal, came up with all these definitions, all these, all this elaborate structure. And that's really where the integral comes from, is from all that stuff, the idea of the Riemann sum. Right, so that, and that's just one other thing too. And that is that when people are asked what is an integral, frequently they'll say, oh, it's area under curve. That's true. It is, that's an application, is the area under the curve. However, another interpretation is that it's an infinite sum. Integrals are infinite sums. And so that's what we're doing here, is we're using an infinite sum of an area to define the integral. All right, so using all that, can we go through and use all that to try and find the volume under a surface and above a rectangular region? Okay, so now again, it's kind of the same idea. If you sit and think about it for a few minutes, and you're like, how can I use this previous result of area under the curve to find the volume of under a surface? Well, area under a curve, we chopped it up into pieces and added up the area of those pieces. Maybe volume under a surface, you should chop it up and add up the volume of those pieces, right? So hopefully that makes sense as a reasonable starting point, right? And so in terms of chopping it up here, how could we chop this up? Well, I mean, again, this is maybe another thing that take you a few minutes if you thought about it, but the best way to chop it up would be to cut up the base here. That's what this is called, right? The base. To cut up the base, this rectangular base, into rectangles, and then find the volume that's directly above each one of those little mini rectangles, and then add those up. It's kind of the same idea as taking the base here from A to B and cutting it up into equal sized pieces, right? And then finding the area that's above each one of those pieces, right? You can think about it that way. So we want to do the same idea here, except, instead of having a one-dimensional piece that we're cutting up, we're going to have a two-dimensional piece. All right, so what would that look like, right? So we could go through and try and draw that on this picture. I'm going to do my best here. I'm not sure how well this is going to work, but we could go through and we could say, all right, there's a piece, right? And then we could find the volume that's above that piece. And similar to area under curve, you could use any place inside of this rectangle you could use to figure out what the height is. I think I'm going to use this corner here. It doesn't really matter what you use. Okay, that's not too bad. All right, so we've got, oh, and there's one more. So we've got a volume of a little box there, right? Rectangular box. And so that could be part of the volume that's under this surface and above our base, above our rectangle. All right, so next you could go through and you could cut out another box, right? So at some point this is going to turn into a disaster probably, but that's okay. And so that box looks a little too big for that one, but that's all right. So you just use your imagination. All right, so now we used the left corner here The left bottom corner is the height, so we want to use the left bottom corner. We want to be consistent, so use the left bottom corner for the height of that box. And it's the angle, but it looks like it's the same height. It's not the same height. This is going upward. And so we get another box. So we take the volume of that box, add it to the volume of the first box. Let's do one more, and then we're going to say that's good enough. You get the idea. All right, so the next box, again, the height is going to come here at this corner. Okay. So you get the idea, right? So we're going through and we're adding up the volume of these boxes. Now you could go through and chop up the base into pieces, add up all those volumes, and that would be the same thing. You know, if you just did it with a handful of boxes, that'd be the same thing as our first step in finding the area underneath this curve, where we might have chopped this up into like 8 rectangles. You know, if you went through and chopped this up into, I don't know, it looks like maybe this is 3. It looks like maybe the dimension, maybe there's 4 across. If I chop this up into 12 little rectangular boxes, you could add those up. You know, but what we want to do is we want to just skip over a lot of those intermediate steps that we did in Calc 1 and just kind of try and fast forward as much as possible to the end where we have the Riemann sum equivalent. So the thing that's going to make this problem different from the previous problem, the main thing that we're going to focus on, is the previous problem we had from A to B, and it was kind of maybe not obvious, but there weren't a lot of options for how to go through and cut this up. It's a number line. If you want to think about it, it's the x-axis that you're chopping up, and there's really only one way to do it, just from left to right here. If you're going through and taking the base here and cutting it up, there's a lot of different ways that you could do it, as I'll describe in a few minutes. And so what we want to do is we want to focus on that as our next step, is thinking about how are we going to go through and break up the base, you know, to end up adding up the volumes that are above it. All right, so to do that, what I'm going to do is I'm actually going to pretend I'm looking straight down, right? So if you were hovering above this object and you looked straight down on it, right, you would see this rectangle. That's what you'd see if you looked straight down. So we want to go through and just draw that rectangle in a separate picture, where you're looking straight. If you're looking straight down, you wouldn't see the z-axis. You'd just see the x and the y-axis. So what would we see? If you looked straight down, you'd see A, B, C, and D, and then our rectangle. And so what did we do in this case? We went through and we cut the one part of this rectangular box. We chopped up and added up the volumes that are directly above that. So the equivalent on this picture would be like slicing across like this, and then we broke it up into 3 pieces, right? So maybe one, something like that. Those 3 pieces are these 3 pieces. Okay. So to try and go through and make this more formal, what we want to do is similar to what we did in the Calc 1 cases. We want to go through and, you know, create like an x sub I type thing and say this is x sub 1. This is the first rectangular base. This is the second. This is the third. And so that's what we want to do next, is we want to go through and do that. Now, the thing that makes this more complicated is we have 2 dimensions instead of just 1. So what we're going to do is we're going to go through and just pick a spot here in this, and well, maybe the best way to do this is just to kind of pick a spot. You could pick the middle, you could pick the corners, it doesn't matter. But what we're going to do is we're going to pick a spot, and we're going to say this is the x sub 1, y sub 1 box. And we're going to say this second box, actually we could just, I made them big enough you could write it inside. This is the x sub 2, y sub 1 box. And this would be the x sub 3 y sub 1 box. Now, why have I kept the y's the same while varying the x's? It's because of the fact that this, if you think about the way that we're doing, that this series of boxes has this is across from the same y value, right? It's across from here. So that's why the y value doesn't change. But the x values, this first one, you could think about it like it's here at x1. The second one, you could think about it like it's here at x2. And the third one, if you did it at the center, it's here at x3, right? And then if we went through and did more strips, right? What would the next series of strips look like if we went through and labeled them? This next one would be, now we'd have x sub 1, right? X sub 1. And then now we've changed y, so it's going to be y sub 2. And then this one would be x sub 2, y sub 2. And then this one would be x sub 3, y sub 2. Okay, and so that's the way that we could go through and maybe organize. We want to organize this structure in which we're going through and adding up the volumes that are above these boxes. So we've got to organize the boxes that are directly below them before we can add up the volumes. Okay, so now that we've done that, right, so you can see how that works, the next thing that we want to do is to go through and do the equivalent of this generic box. This generic rectangle from Calc 1, right? So so that's what I'm gonna do next. I'm gonna take this idea here where we just said, all right, we got it. This is x1, this is x2. So I'm gonna say there's an x sub ith box, a rectangle. I'm an x sub ith rectangle. It's got a base, it's got a height. I can multiply them, create an area, and then sum. All right, so let's do that next. All right, so what I'm gonna do is I'm gonna go over back to my picture over here on the left, and I'm gonna say, all right, now I'm gonna assume there is an ith. Well, maybe not ith. I'll explain that in a second. I'm gonna assume that there is a generic box over here. And if you go directly up from that, you're gonna hit the surface. And it doesn't matter what you use for the height. It could be the left corner, the middle, just as long as it's consistent. All right, and now this generic one, using the ideas over here, what I'm going to say is that's this generic one, I'm going to say it's at x sub I comma y sub j, right? Instead of just x sub I from the area under the rectangle, we only have one dimension here, so we didn't need a second one. Here we've got two dimensions for our base, so we need two coordinates. And as you noticed when we went through and just tried adding up tried going through and labeling where the boxes would be, the coordinates are different, right? So you could end up, varying the ith coordinate and keeping the jth coordinate constant, and that would end up adding up these boxes in a row along the x-axis, right? And then you could change j, and then you could vary I again, and then you could change j and vary I again, and change j and vary I again, right? And so we need to have a coordinate system where we have two different values. Okay. And now the next part, what did we do? What did we do after we went through and labeled x sub I? Here, we went through and said, all right, well, the width of the rectangle is going to be change in x, and the height of the rectangle is going to be f of x sub I. All right, so the next part, let me try a different color because my picture is going to get a little messy here. So the next part, we could go through and label. So we could say this distance here, right, is along the x-axis. So we're going to call that change in x. This distance here is along the y-axis, so we're going to call that change in y. Actually, I'm going to put it on this side, though, just to think it'll end up behind all those lines if we put it on that side. So we get change in y. And they are different, all right? So this doesn't have to be a square box. It could be a rectangle. You notice I drew them kind of like rectangles here, and I drew them like rectangles here. They don't have to be squares. And then finally, the height of the box would be f, right? And then what we're doing is we're taking our coordinate x sub I, y sub j, and plugging it in. So we're going to have f of x sub I, y sub j, like that. Oh, and the one thing I forgot to label is that this curve is, if kind of not obvious, it's z equals f of x comma y. And so just take the point where the where your box is located, and then you plug it into the function, and that gets you the height. All right. And so now if we take all that and put it together, you've got the height of the box, you've got the width and the length of the box. That means you could find the volume of the box by multiplying them. So we get f of x sub I, y sub j, change in x, change in y. All right, and so now we've got, that's the volume. Once we had the volume, once we had the area in Calc 1, we then went through and put a sum, and the sum, well, not only added up the boxes, but because of the way our summation symbol works, it incremented the I value so that you crossed from one side of the area of the region you're finding the area of to the other. So that's what the summation symbol does, is it not only adds up the rectangles, but it also has this system where it takes the I and increments it, and the I here is the location. So we want to do something similar here. So what we're going to need to do is, if you'll notice, the way that I wrote out the example we did earlier with the rectangles is that we need to go through and vary the I and keep the j the same, and then vary the j, and then do another strip of varying the I. So how could we do that? Well, the way that you could do that is with two summations. So you could do I equals 1 to n, j equals 1 to m. Okay, and now if you actually sit down and look at how this works, so what's going to happen here is that you're going to start off with this outer summation. It's going to say j is 1. All right, so the whole thing, the whole sum doesn't happen. It just says j is 1, and then you move to the next summation, and it says I is 1, and you go through and take and calculate the value for I is 1. Then you increment I to 2, add, increment I to 3, add, all the way to I to n, add, and then when you're done with that, it's kind of like there's parentheses here. When you're done with that, you then work your way back to the outer summation, and then it increments j to 2, and then you do I to n, j to 3, 1 to n, j to 4, 1 to n. And so what it does is it adds up across this exactly the way that I kind of labeled it, where you're getting this effect that's almost like adding up in strips. So let me again use a different color because I'm going to draw on top of this. So it's like you're adding up this way. Okay, with the way that I've labeled this, you know, or if you want to do it on this picture, you're adding up this way. Okay, and so put it all together, and the double summation is the way that we can go through and add up across this rectangular box. So you've got one dimension for the base, one sum. Two dimensions for the base, you need two sums, one to add across, and then the other one to increment so that you then add it up in these strips. All right, and then the final thing that we did in Calc 1 is, once we went through and kind of formalized all that stuff, is we said, well, you know, if you pick a finite value for n, then you're going to get a finite approximation for the area. Let's take n and have it go to infinity. That will make it into an exact area. And so we're going to do the same thing here. If you put finite values for m and n here, you'd end up finding a finite approximation for the volume that's under the surface. And so we can go through and throw a, I'm still using red. Let's erase that. Let's go through and make that the limit as m and n goes to infinity. And boom, you're going to get the exact volume. All right. And that's the derivation for this formula. All right, it comes from all the stuff that we just finished discussing. Now, as far as how to use this formula to go through and find areas, to find volumes, what we're going to need to do is we're going to need to find a way to turn this into integrals. All right, so I'll show you how to do that. It's kind of cool, or at least I think it's kind of cool. What we're going to do is we're going to rely upon this definition here from Calc 1, and then we're going to use that to go through and translate this into integrals. But okay, so that concludes kind of this derivation up to this point. Next, we're going to focus on how do we manipulate this into integrals. So it's kind of the second step. All right, so let's start there. So we've got the limit m, oops. M and n to infinity. We have sum I equals 1 to m, sum, that's supposed to be a j, I equals 1 to n, f of x sub I, y sub j, change in x, change in y. Okay, so the first thing I'm going to do, actually, that I should have done probably when we did the derivation here, is that you can go ahead and have little stars on these to represent the fact that there's more than one possible x sub I value that you could use. You could use the left side of the box or the right side of the box, or the midpoint of the box relative to the x-axis. And then the same thing for y. So you can put stars here just like you do in the Calc 1 setting. All right, so the first thing we need to do is we need to split up this limit. So we're going to split up the limit. We're going to have a limit m to infinity, and then we're going to have another limit n to infinity, and then a sum, the first sum, j equals 1 to m. And I can't draw sum symbols with this writing tablet unless I do it really slowly. I equals 1 to n, f of x sub I star, y sub j star, change in x, change in y. All right, so we're splitting them apart, and we're saying we're going to take the limit as m to infinity first and limit as n to infinity second. All right, so this outer limit as n goes to infinity, it does not change, it does not affect this summation here. And so because of that, you can bring it inside the summation. So we can rewrite this. So the limit as m goes to infinity of the summation j equals 1 to m, and the limit as n goes to infinity, the summation I equals 1 to n. Oh, and there's one other thing. So many details. It's easy to forget some. All right. Just like in Calc 1, we went through and we labeled what these are. You can do the same thing here. So you could say x sub I star is equal to a plus I change in x, and change in x equals b minus a over n. And then you could say y sub j star equals c plus j change in y, and then change in y equals d minus c over m. If you go back to the previous pages, those all kind of make sense. All right, so we get to this point. Now the key here, the key to understand once you're at this point here, is that there's an order that events happen. You choose a j value, you then go through and do this whole inner thing. You then increment the j value, and then you do this inner thing. You then increment the j value again, and then you do this whole inner thing. Now, what is happening each time? Well, when j is 1, you're picking a value for y sub j. So it's going to be y sub 1, right? And that value stays the same throughout this entire inner calculation. You're going through and you're adding up all the values So you're going to have y sub 1 here, and then x sub I is going to go from all the way from 1 all the way to n. The whole time it's going to be y sub 1 the whole time through an entire strip here, right? And then once you get to the end of that, you're then going to say, okay, I've calculated this whole inner thing. I've got some number. All right, cool, I'm done. And then you go back to this outer one, and then j increments to 2, and you start all over again. And the whole time you've got y sub 2 is the same the entire time. Right. So if you think about what's happening then is that when we're doing this inner calculation, the y is constant. It's going to be y sub 1 for the whole for this whole calculation inside this parenthesis. And then you're going to increment to y to 2, and then it's going to be y sub 2 the whole time. And so what we've got here is that y is acting like a constant, all right, inside this inner thing. And so you really could go through and replace this definition, at least temporarily. We could go through and say, you know, I'm going to take h of x sub I star, and I'm going to say that it equals f of x sub I star, comma, y sub j star. And so that's because that the y sub j is constant inside that inner calculation. And so I really have a function that is only varying with x. And if you go through and do that, you fill that in, you get the limit as m goes to infinity. We get the sum j equals 1 to m. And then the limit as n goes to infinity. I equals 1 to n of h of x sub I. So because y is a constant, inside this, now it's not a constant throughout the whole calculation, but just inside this, we're compartmentalizing here. Just inside this, it acts like y acts like a constant, and so we can just drop it out of the function. Then you get h of x sub I star change in x, and I'm going to take this change in y, and I'm going to like kind of factor it out and put it out here. Now it doesn't go all the way out, but it's something like this. All right, so now take a look. What have we done? By doing that, so since y is a constant inside this inner parenthesis, and we can replace this function with 2 variables into a function with 1. Now look at that. That right there is our Calc 1 definition for an integral, right? Look at it. Limit, sum, f of x sub I star, change in x. Boom, you could just drop it and turn it into an integral. Limit, sum, h of x sub I star, change in x. So boom, you can just replace that with an integral right in the middle. So we get this doesn't change, and then this whole inner thing, I'm going to now then replace it with an integral. It's the integral, right, of h of x dx. Then you've got this change in y that's still hanging out here. Okay, and then what was h of x? Well, if you take h of x and you put x in place of the x sub I star, then you're going to get f of x comma y sub j star. So we can take that and rewrite it as the limit m to infinity sum j equals 1 to m. This is the integral of f of x comma y sub j star, right, dx, change in y. Okay, and now at this point, right, so think about what's happening here. We just kind of put some parentheses around this. We've got this so what happens, right, when we go through and calculate this? We go through, we pick a j value, we say, okay, j is 1. And if j is 1, then you're going to plug in y sub 1 here. And then when you plug in y sub 1, that's just going to be a number. So you're going to plug in a number here, and then you'll be able to go through and calculate this integral with that number plugged in, right? And when you're done calculating the integral, that's going to be your sum of, that's going to be your sum of volume. And then, for that strip, and then you're going to go through and increment j to 2, and then you're going to go through and plug in y sub 2. That's going to be a number. You're going to pop a number in here. You can calculate this whole integral with a number there, right? And then after that, you're going to do j sub 3. And so what's happening here is that this inner thing is acting like a function where we're just plugging in y sub j values and then producing outputs. Okay, so what we can do is we can replace this with a function. And like, what letter did I use? I already used H. I used P. All right, so let's say then we're going to say P of y sub j star, right, equals the integral of f of x comma y sub j star dx. And if you do that, look at what happens, right? So this becomes the limit m to infinity sum j equals 1 to m. This whole thing is p of y sub j, change in y. And look at that. Again, if you look at that and compare it, this what we said is we said that anything that has this Riemann sum form, we can, boom, just replace it with an integral. So, wrong direction. So anything that has this integral form, we can just replace with an integral. And so we're going to get the integral of p sub y dy. Oh, I forgot some details here. All right, so this integral here should have, since it's x, it should have the x bounds. So it should go a to b, a to b, a to b. And then this integral, since it's for y, it should have the y bounds. It should go c to b. And then last but not least, we can take what our p was. And so this is p sub y. Just take y and pop it in for the y sub j, and you could substitute. And so we're going to get the integral from c to d. And then what is p sub y? It's the integral from a to b of f of x comma y dx. And then you have dy after that. And this is our formula for going through and finding volume under a surface. And what does it look like? What is it called? It's a double integral. And the key to going through and evaluating the double integral is this derivation that we just went through, which is, partly I went through it because it's cool. But another reason to go through it is that it will actually explain to us how to go through and evaluate the double integral. So that the process itself will be useful in terms of figuring out what to do. All right, so let's go through and actually try and calculate one of these double integrals. All right, so let's suppose we have a problem. And we want to go through and evaluate. So how do we evaluate? Let's put some notes here off to the side that we can use to kind of just, so that there's a visual that's going to go with the audio explanation. All right, so when you go to evaluate this, there is an order that you're going to do the integration. And the order is going to be inside out. And that's really kind of the way that you go through this process. So you do these inner strips first, and then you do the outer strips second. So in this derivation, we focused on the interior, on the x first. We went through and replaced the inner part with an inner integral. And then we went through and added the second outer integral at the end. So the inner integral came first in the derivation. So we want to go through and evaluate the inner integral first. Okay. So the inner integral first. Okay, and so you can even put parentheses around here, or brackets. I'm going to use brackets. Like that. Okay, so when you go to evaluate this inner integral, the variable that's on this, so how it says it has dx here. So we'll do another problem with a different, where we don't have dx, where we have dy instead, and I'll talk about what that means in terms of the double integral. But the variable does matter here, and the x tells us what we're integrating with respect to, right? So you have to pay attention to the letter that's next to the d for that inner integral. So next to the d, so in this case dx. Right, so we've got that dx. All right, so what that's going to do is it's going to tell us what to integrate with respect to. Now, if you recall from the last chapter, we talked about differentiating with respect to. Well, in this chapter, we're going to talk about integrating with respect to, right? And so that letter is going to tell you what thing to think of as varying, right? What thing to think of as a variable that's that's changing in the function, and what thing to think of as a constant. All right, and so what we're going to do when we're doing this inner integral with respect to x is we're going to pretend that y is a constant, and we're going to integrate. We're going to just think about it like the x is the only variable. Now, does that make sense? Well, recall when we were going through and doing our derivation, what we said is that we said the y is chosen first, and then you go through and do, and then you vary x to find this inner value. So that does fit with our derivation, is that when we were going through and doing the inner value, we were saying we're going to pretend that y is a constant because of the fact that the y is set by the outer sum, and then the inner sum, the entire inner sum happens before you go back and vary the y again. All right, so this is telling us to go through and vary go through and think of the x's varying for this whole inner piece and pretend the y is a constant. Okay, so we can do that, right? So if you were integrating this, we know how to integrate when we have a constant. The way that you integrate when you have a constant is you just set the constant off to the side, and then you find the antiderivative for what's left. So what we want to do is we want to go ahead and do that. So we're going to take the constant, so that 3 is a constant, but the y squared is also a constant. We're just going to move those off to the side. That's our constants. And then we're going to find the antiderivative for x. So that would be x squared over 2. And then we have from 0 to 2, and then dy. All right, so pay attention to the letter next to the d. In this case, it's an x. So that tells us what to integrate with respect to. Let's write that. All right, and then so once you've done that, you go ahead and integrate with respect to that variable. By treating the other variable as a constant. I'm going to run out of space here. Okay, cheated. I squeezed it in right here at the bottom by treating the other variables as a constant. So that's what we did. Go ahead and finish the integral by plugging in the values. So we're going to get the integral from 1 to 3, 3y squared, and plug in 2, you're going to get 4 over 2, that's 2. Plug in 0, you're going to get 0 dy. And so we're going to have the integral from 1 to 3 of 3y, not 3, sorry, 6, 6y squared dy. Okay, and then after that, the last step is to just go ahead and you have just a Calc 1 style integral left with the other variables, so just evaluate the Calc 1 integral that's left. And that's kind of the process, right? So to do that, we can do that, right? So the antiderivative of 6y squared would be 6y cubed over 3. So that's going to be 2y cubed, right? Oops. I shouldn't have drawn my integral symbol again there if I'm going to do the antiderivative. So we're going to have 2y cubed and then evaluate it from 1 to 3. And then you can go ahead and plug that in. So you're going to get 2 times, what is that, 27 minus 1. So we're going to have 2 times 26, that's 52. Okay. And I just looked at my notes and I got a different answer in my notes. So that's great. But I'm pretty sure my notes are wrong. All right. So that's how we can go through and evaluate double integral. Let's do another one. And then we're just going to go through this process on the next one without, of course, writing it all down. If you need to, you can just refer back to this page for the steps. All right, so we have 0 to 2, 0, oh, whoops, sorry, 0 to pi over 2, and then 0 to natural log 2, and we get sine x e to the y dy dx. Okay, so just like the last one, you can go through and you can kind of break it up. Say, all right, break it up into 2 pieces. Now this time we have a dy. All right, so what does that mean other than when you go through and do the integral? When you find the antiderivative, we're going to integrate with respect to y, which means we're going to treat the x as a constant. What does it mean other than that? What does it mean if you actually go back to our derivation? It means if you went back to the derivation, these two are reversed. And it means that you're varying y first, and then you're varying x second, right? So you'd have i's here and j's here. So we're going to be adding up in strips across that are where y is changing first, and then x is changing second. So what does that mean as far as our problem? If you went all the way back to our problem, our initial problem, it means that if you were to go through and think about it, if we vary y first, then you'd be adding up in strips that went this way. Can you do that? Is that okay? I mean, can you add up across a rectangular box instead of doing strips this way? You could do strips this way. Of course, why not? Yes, of course you could go through and vary y first and then add up strips this way instead of adding up strips this way. And so because of that, it's perfectly okay to reverse the y and the j. I'm sorry, the x and the y. The y and the, well, it is the I and the j, or the x and the y. All right, so these two in total, these two together are called the order of integration. Okay, and so the previous one, we did strips in the x direction, and then this time we're doing strips in the y direction. And so in terms of evaluating this, the only effect that has is that we're going to go through and pretend that x is a constant first instead of pretending that y is a constant. So if x is a constant and we're integrating this problem, then the x just drops down, right? So we go from so sine x is a constant, so the antiderivative is sine x, just going to drop down, and then we're going to integrate the e to the y dy. So what's the antiderivative e to the y dy? It's going to be e to the y. Then we get 0 to natural log 2 dx, and then you could plug in. You get the integral from 0 to pi over 2. This is sine x. We get e to the natural log 2 minus e to the 0 dx. So e to the natural log 2 is going to be 2. E to the 0 is going to be 1. So we're going to have, this is just 2 minus 1, and 2 minus 1, of course, is just 1. So we can just get rid of all that. And then here, what's the value of the integral from 0 to pi over 2 is sine x? So this is just a calc 1. So after you do your first integration, you should end up with just a calc 1 integral, right? So evaluate the Calc 1 integral that's left. That's what should happen. Now, if you've got variables that are in the bounds here, then something has gone wrong. That should not happen. All right, so it's the antiderivative of sine. It's going to be negative cosine x, evaluated from 0 to pi over 2. So we're going to get negative cosine pi over 2 minus another minus, so plus cosine of 0. So this is negative root 2 over 2 plus 1. Okay, and so that would be the value that we ended up getting. Okay, so just a couple comments here that I want to make before we move much further. Just some little details, right? So keep in mind, this is still volume beneath the surface. This 52, that's the amount of volume that's under the surface defined by 3xy squared over the rectangle that's defined by these bounds, right? So it would be difficult to go through and graph 3xy squared. I don't know exactly what that would look like. But what you can do with these problems, if you want, is you can just graph the rectangle, right? So notice how when I went through and did the derivation of this, I started off with my three-dimensional picture, and I went through, and at a certain point I said, you know what, let's just focus on adding up across the rectangle. So you can go through and you can do that, and that will actually be something that we will end up doing in the next section. So you can, if you want, is to go through and maybe just draw a little picture, but you don't draw the whole object. You don't draw the three-dimensional object. What you do is you just draw the base. So the base goes from x goes from 0 to 2, right? So we've got 0 for x, and then 2 for x, and then y goes from 1 to 3. So we've got this is the base of our object, and you can even go through and label it as such. This is the base of the object. It's not the whole object, it's the base. Okay, is this rectangle. And then one other detail, actually, before I move on to the next picture. I'm just going to do the same thing in the next picture. One thing that might be helpful when you're going through and doing this is if you get confused when it comes to the bounds of your integral, you can label them. So sometimes I do this. So this, since you've got dx here, that means that these are x bounds. This one, I don't know where I might put this. Oh, let's just do it this way. X equals 2. And then these are y bounds. How do I know? All right, so the dx, which is we're integrating with respect to x first, that tells me these are x bounds. dy is second, that tells me these are y bounds. All right, so here, these are going to be which are they? Are they x or y? Well, we're integrating with respect to y first. That means these are y bounds. And then these are x bounds. And then if you were to go through and sketch this, you wouldn't sketch this object. I have no idea what sine x e to the y looks like for a surface. But what you can do is you can just draw the base that's beneath that surface. All right, so we can go through and just say, all right, well, here we've got x. Here we've got y, here we've got x, and then x goes from 0 to pi over 2, and then y goes from 0 to natural log 2. And so the base of our object looks like this. This is going to be good practice because in the next section, we're actually going to need to go through and draw the base of the object. Okay, and so I think that covers all of the basics so far. Let's move on. Next thing, right? So because the order of integration can vary, sometimes you could do dy dx. Oh, let me say one more thing here. The order here doesn't matter. Now, it will matter in later sections, but I want to be clear here that if you change the order on this, it doesn't change the volume. You're still going to be finding the volume under the same surface. The order just is determining whether you do the red arrows first or you do the blue arrows. If you're doing strips that go this way or strips that go this way, you're still going to get the same volume. You shouldn't get different answers if you do different orders of integration. Okay, I just want to be clear about that. It's kind of an obvious thing, but it's something that it's not obvious until you think about it, right? So, and so because of that, because the order can go either way, what we're going to do is we're going to introduce some notation for that. So let me give you the double integral definition, the generic one. and then we can talk about the notation. All right, so because the order of integration can be dy dx, or dx dy, or dy dx, but the value does not change, we introduce a generic notation for that. We introduce a generic notation that could represent either one, dA. So when you see dA, you know, in books or in homework problems, dA is just a stand-in for either one of these two. It could be either one, depending upon you know, which order you want to integrate with respect to first, right? And so what happens here is we get our limit as mn goes to infinity. We've got our summation I equals, hold on, that's supposed to be a j. J equals 1 to m, I equals 1 to n. We've got f of x sub I star, y sub j star. And then we're going to do change in a, all right, instead of change in x, change in y, or change in y, change in x. And then we'll say that that equals the double integral of f of x comma y dA. And then here, because the order could be either one, we want to leave that unlabeled for now. And so we're going to put r. Okay, now the only thing that's goofy about this notation, I know that the summation here, you've got j first and then I, so it kind of implies it's dx, dy, or change in x, change in y. But these are interchangeable, so these could be interchanged. And so that's there's no combined notation like there is with m and n here, or change in a here. You can't combine these into a single summation. And so because of that, we're just going to leave the order like there's an order here, but the idea is that they're interchangeable. All right, so this is like a master notation that handles both of the two orders of integration. So change in x, change in y, change in y, change in x, or dx, dy, dy, dx, depending on how you want to think about it. Okay, and then so the r describes the base. I don't know where the r comes from, region maybe, you know, but that's the idea. So this is kind of our generic definition for a double integral that covers all the different possibilities. So here's our generic definition. Let's go through and try a couple problems using the generic definition. All right, first let's go through and try the following problem. Say we have a double integral x squared over x cubed plus 2 times y dA over r, where r equals xy. And y goes from -1 to 2. Okay, so with a problem like this where the order of integration is not already given to you, what you need to do is you need to go through and choose the order of integration. Now the way that my recommendation in terms of choosing the order of integration would be to go through and do the easier integral first, and then just hope that maybe in doing that easier integral, it might simplify the other integral to some degree. So if you look at these two variables and you had to choose between which thing would be easier to integrate with respect to first, if you do x, you're going to have a u substitution. If you do y, it's just a straight integral formula, right? It's a straight antiderivative formula. We have a formula for integrating y to the first power. So the y would be easier. So because of that, I would integrate with respect to y first. And it's possible that maybe in integrating with respect to y, it might make this second integral so that it's not a u substitution and something a little bit simpler. So that's the way that I go through and do it, is I do the easier integral first. All right, so we could just rewrite this. This is x squared y over x cubed plus 2 dy dx. And then we can put our y bounds on here. So -1 to 2, and you can label them. We get y equals, and then x equals 0 to x equals 1. Okay. And now we can go through and integrate this. And so when we're integrating with respect to y, we're going to pretend that x is a constant. So what you have, this whole thing is just a constant, everything except the y. And when we integrate, what do we do with constants? We just ignore them. I mean, well, not ignore them, but we just drop them down in the formula, right? We don't integrate them. We just kind of move them off to the side. And then so once we've done that, we can actually go through and do the y antiderivative here. So we would get y squared over 2. And then that's going to be evaluated from -1 to 2. And then we'll have dx. And then you could plug in 2. And if you plug in 2, we're going to get 4 over 2. That's going to be 2 minus, then we could plug in -1, and we'll get 1/2. And if we simplify that, we get 0 to 1, x squared over x cubed plus 2. 2 minus 1/2 is going to be 3/2. We could just move that out front. And then we have dx left, right? And so here's our Calc 1 integral that's left after we do our first integration. And so unfortunately, our integral, it didn't make the integral any simpler to do. We still have a u substitution here to do, but we can do that, right? So to do that, we'll go through and set u equal to x cubed plus 2, du equals 3x squared dx. And then our integral is going to be 3/2. When we change, we're going to change the bounds here. The bounds here are in terms of x. We're going to change them over to u. To do that, you just want to take the bounds and plug them into your substitution. So if we take 0, plug it in, you get u equals 2. Take 1, plug it in, you get u equals 3. And then once we're done, we're going to have here in the denominator, we have u. And then the numerator, okay, so the thing that we have to do with the numerator, so if you look at the numerator, we need 3x squared dx. Right now we have x squared dx. So what you need to do to fix that is you need to multiply by a 3 and then offset it with a 1/3. All right, so if we do that, then we're going to need another 1/3 over here to do our offset. And now here we've got 3x squared dx, that's our du. Okay. And then once we're done with that, we can go through and evaluate this new integral. The 3's here cancel. We get 1/2. The antiderivative of du over u is natural log u, evaluated from 2 to 3. And so we're going to get 1/2 natural log 3 minus natural log 2. And that's our answer. Okay, so that's how you go through and you handle an integral where the order is not specified. If you've got r and dA, then you've got to choose. And what I do is I go through and I choose the thing that's easier to integrate first is the one that you want to do first. All right, let's try another one. So you may see this notation, this shorthand notation at times, depending upon the problem sets that you're working on. What this is this is just the x bounds and this is the y bounds. We're just doing x by y, and so whatever bounds here that you're using, these are the x bounds. So it's just a shorthand version of this. So instead of writing out the set builder notation like this, we've got 0 to 1, -1 to 2. Instead, they just get lazy, and then they just write x by y, where they put the x bounds first and the y bounds second. Okay, so we need to go through and choose the order of integration. If you look at this problem, you've got an x times sine of xy. If you were going to integrate with respect to x, because you have x in two different places like that, right, this is going to be an integration by parts problem if you integrate with respect to x first. Okay, so right when you've got a product with two different functions, then typically you've got to integrate by parts. However, if you just integrate with respect to y first, right, then x is treated as a constant. So if you're integrating with respect to y first, it's essentially like you would be doing this problem, all right? Right, so you just pretend the x's are constants. So if you throw some constants in there, you can actually look at it. If you had this problem, this is not integration by parts. This is just this is a u sub. I mean, it's not a super simple integral, but it's just a u substitution. And so it's definitely less complicated to do the y first. So my advice is, if it's less complicated, the variable that's less complicated is the one we want to do first. So we're going to do x sine xy dy dx, and then the y bounds here are going to be 0 to 2. And you can label those. And then the x bounds are the other bounds. And so we've got 0 to pi over 6. Those are our x bounds. Okay, and now to go through and do the integration, just like if we were going to do this problem here, we have to set u equal to 5y. So of course it's not, x is not 5, it's x. So we want to set u equal to xy. And then if we take the derivative of both sides with respect to y, we would get du equals x dy. All right, so that's our substitution. All right, so then we're going to have 0 to pi over 6. And then we're going to change the bounds here. So instead of 0 to 2, you could take 0, plug it in. Right, and if you take 0, plug it in for the y, you're going to get 0. If you take 2 and plug it in for the y, you're going to get 2x. Okay, and then our function itself, we've got sine of xy. That's going to become sine of u. And then we've got x dy. That's du. So we're going to replace that with du. And then we'll have dx left. Okay, so these are now u bounds, not y bounds anymore. These are still x bounds. All right, so find the antiderivative of sine u. Right, that would be negative cosine of u. Evaluate it from 0 to 2x dx. And let's go through and move this over here. So 0 to pi over 6. And then if we plug in 2x, we're going to have negative cosine 2x. And then minus a negative, so we're going to have plus cosine of 0. All right, so that's going to, we'll have 0 to pi over 6, negative cosine 2x plus 1. Right, so because here we still have dx left. And dx. And then the antiderivative of negative cosine 2x would be negative sine 2x over 2. The antiderivative of 1 is plus x, 0 to pi over 6. So plug in pi over 6, we're going to get negative sine pi over 6 times 2, we're going to get pi over 3 all over 2 plus pi over 6. And then we have minus, and if you plug in 0, sine of 0 is 0, and 0, x equals 0 is just 0. So we don't need to, when we plug in 0, we just get 0. And then sine of pi over 3 is going to be root 3 over 2. So we're going to have negative root 3 over 2 over 2. That's going to be over 4 plus pi over 6. And that is our answer. Okay. So there's a second example. That's two examples of going through and choosing the integration order. Now, would you get this problem wrong if you go through and do the integration by parts first and then do the y second? No, I don't believe so. You should get the same answer. I haven't tried it that way, so I don't know, how easy the problem works out. But you should be able to go through and do it that way and still end up getting the right answer. So you're welcome to try that for fun. But I would recommend doing it this way. I think this is the easier way to do it. Okay, so that concludes our first video for double integrals. So we're going to have more double integrals to come in future videos. Thank you for watching. See you next time.